Hi folks, Aaron Harper here for the third part of the link budget. This one's going to be more mathematically heavy, and if you're anything like me, you really need a refresher on some of the trigonometry that you did in high school or college. So that's what we're going to do today, and then we're going to apply it to the propagation segment of the link budget. The next video will be using the data that we generate this time and applying it in order to find out exactly how much free space propagation loss there is in this particular segment. The first thing is that if I don't do a really good job explaining things, you probably need to go see another YouTube channel. Go to Khan Academy, and the two things that we're going to cover here is the law of sines and some of angles portions of trigonometry. I'll do my best to explain it, but I'm not a teacher, and we'll get through this between us. The problem comes from the fact that the Earth is round, in contrast to what some people think. And we just happen to be, pardon my stick figure, we happen to be on one part of the Earth. That's where we observe. Now, ISS, my little generic spacecraft symbol there, is flying high above the Earth. In fact, it's flying at 400 kilometers above the Earth. But what is actually orbiting is the center of the Earth. There's the radius of the Earth, and this section of it is 400 kilometers. Interestingly enough, the radius of Earth is a known number. It is 6,378 kilometers to the actual center point where where ISS is rotating around, and quite frankly, so are we. We just happen to be standing on the ground. So that means that our point is also 6,378 kilometers. This particular section here is a combination of the two, so that plus that yields 6,778 kilometers. So that's all fine and dandy, but our question actually is, what is the range to our target? What is the distance between the observer or his ground station and ISS? Well, we don't really have that. Not yet. But okay, so our observer is right there looking at ISS, and pardon the incorrect angles, but this is obviously not to scale. The angle of observation is an elevation above the horizon of, let's say, 60 degrees. That means that from the horizon to this angle here is 60 degrees, and from here back to the ground, from the horizontal point of the ground, is perpendicular to the line going to the center. So therefore, there's a 90-degree, a right angle there. So this angle in our triangle is actually 60 degrees plus 90 degrees, which comes to 150 degrees. So let's restate this on what we know of this triangle. Our triangle has a length, and what we'll do is we'll call this A, and we'll call this B, we'll call this C, and we will label the sides opposite of the angles with the lowercase letter. So this becomes C, this becomes A, or actually that should be lowercase, right? And this becomes B. So what we know is that the length of segment A is 6,778. We're not going to put down kilometers right now, but we'll bear in mind that we're dealing with units of kilometers, in other words, 10 to the third. We also know that angle A is 150 degrees. Finally, we also know that segment B is 6,378 kilometers. Well, it doesn't really give us the information we need for the length of segment C. That's where the trigonometry or law of sines comes in. And unfortunately, this is going to be a three-step process in solving it. So, okay, first of all, law of sines. The law of sines simply states that the sine of A over segment A is equal to the sine of B over segment B is equal to the sine of C, and all these are angles, over segment C. It simply is an equality of the three things. So if we have one, we can derive the others. But we need either the angle or the side to figure out the other through algebra. So what do we know? We know A is at 150 degrees. We know B is 6378. And we know A is 6,778. Well, it's rather convenient that we know the angle and the segment. We know both of these. So what can we derive? Well, the only thing about the other sides and the other angles we know is we know that the segment B is 6378. So from that, and using the law of sines, we can derive the angle B. Still not where we want to go, but we will get there, I promise. So let's restate this. What we're after is the angle B. So we'll say the sine of B over segment B, which is 6778. Nope, sorry, 6378. This is B. 6378 is equal to the sine of A, which is 150. So sine 150 over the segment A, which is 6778. Well, that looks like a solvable equation. So let's go ahead and start paring down this math. The parts that we know is that if we plug it into a calculator, the sine of 150 is 0.5. So we can tell that sine B equals 0.5 over 6778. That's sine B over 6378. So let's put a 1 over there. So let's multiply the whole thing by 2, and you get sine B over 6378 is equal to 1 over, I got to refer to my crib notes here, 13556. Well, for our next stunt, if we multiply both sides by 6378, what do we get? Well, sine B is equal to 6378 over 13556. Okay. Our next step will be to move the sine function over here. So now, therefore, B is equal to sine -1. And then we can go ahead and solve this, which comes to 0.47, and I think this is 0. Can't read my writing. $4,705. Well, let's plug that into a calculator, and we have the look down angle from ISS to here. In other words, we have this angle, we have B. Doing that math, we have B is equal to 28.066 degrees. So there you go. Well, we've gotten one side figured out, actually one angle, but that still doesn't give us what we need. But like I said, it's a 3-step process. The next step is to determine one of these, preferably this, but we can't quite get there from here. What we need is to find out the angle. Now, the interesting thing is, according to the sum of angles, all the angles on a triangle sum up to 180 degrees. So therefore, since A plus B plus C equals 180, we can derive that 180 degrees, or excuse me, that C is equal to 180 degrees minus 150 degrees, and then minus 28.066. What becomes of that is that we can find C, and that C is equal to, looking at my notes, 1.934 degrees. So there you go. Now that's not really a surprise, because with a 60-degree lookup angle and winding up with 150 degrees worth of your 180 degrees there, you're going to end up with a fairly acute look-down angle of 28 degrees and an incredibly acute angle at the center of the Earth. Given that the center of the Earth is, from our perspective here, well, not here, considerably higher than most folks, is 6,378 feet, or excuse me, kilometers below sea level. This means that the distance here is quite large, which would put the angle at a very, being very small. So that basically covers the sanity check and the fact that they add up. The interesting thing is, though, that when you do such a thing, there are usually 2 points where the where everything adds up, or at least one side of it. If you're strictly dealing with sides, and not angles, there is a point where the sides or the angles may match, and there's also a point if you're strictly doing angle or if you're strictly doing sides where the angles match, but never both. So when it's done, you sort of have to do the sanity check by adding the angles, making sure everything, makes sense. We call it a sanity check, but there are other ways of pointing this out. The bottom line is, look at it. If it makes sense, great. If it doesn't, do it over. The next step, though, is we still have not identified C as a segment. In other words, we have not figured out the range to our target. And that's what comes next. We're going to refer back to our old friend law of sides. And here's the question, what do we know? We know that C, we know the angle. So therefore we can get the ratio. We also know the angles A and B, and we also know the segment length of B and A. So we could use any one of these. But let's use the one with the largest number, that being segment A. So, law of sides, and we'll go ahead and put a line here. Law of sides dictates that the sine of C, which is sine of 1.934 over C is equal to the sine of 150, which we already know is 0.5 or 0.5, over this here, 6,778. From this point, we solve. But it's a little bit more complicated because instead of solving for the numerator, we're working on the denominator, which it's a thing. So the next step is to do some reduction. So the first bit that we're going to do is pop C out of there. So if we stand by here, I'm going to get my notes where I can see them. If we take and the first thing we need to do is make sure that looks right. And so, basically put a 1 at the top. And the second is, let's go ahead and pop the sine function out of there and where it belongs. So we will have C is equal to 1 over the sine of 1.934 times 13556. Let's extend our line there. Well, that looks solvable. So when we finally do this, C is equal to 457.42 kilometers. We have just solved this 457.42 kilometers is the range here. Now, the question is, what good does it do? The truth of the matter is that this allows us to know exactly how much loss we have of the signal. In the first video, I mentioned how if a candle is close, you can read a book by it. But if a candle is miles and miles and miles away, you might not even be able to see it. For example, if it's on the side of a distant mountainside. So this segment here and its length has by far the biggest determination on exactly how much signal you get. The amount of attenuation based on distance, your free space loss, is the big deal. It is the thing that makes or breaks whether or not a link budget works, more so than any other component. You know, originally we were complaining about 0.5 dB connector losses, 0.05 line loss, maybe an antenna mismatch loss of half a dB, and so on. This distance, the free space propagation loss of this distance, is in the hundreds of dB. That's why we need to generate one big signal. That's why we need to amplify it when we receive it. And that's why we need gain on the antennas. But if we can traverse that piece, not only physically, but with our technology and with our ability to receive that signal, we can functionally be in space. We can do things in space. We can receive signals in space, and space works for us. How that actually applies and the math behind it is what comes next, so stay tuned.